Life has existed on one planet for about 4 billion years, as we know. But it could have started right after the Big Bang, when the universe was much stranger and more fantastic than it is today. This universe, possibly influencing the growth of life everywhere. Space may be full of life embryos, lying in a deadly war, waiting for a few drops of rain to suddenly bloom and grow. Small and not so small aliens could be everywhere. To explain this correctly, let's first consider the paradox of life on Earth. The paradox of life. For the first few 100 million years, Earth was a magma hell, constantly bombarded by asteroids. But essentially, as soon as everything calmed down and the first oceans appeared, life simply emerged. And millions of microbes settled in every nook and cranny they could find. This is quite strange. Life on Earth seems to be almost as old as the planet itself, as if it was waiting for its chance. But life not only appeared extremely quickly, in this small time window, it also bridged a huge gap. Even for microbes to be considered living beings, they need to eat, excrete, grow, and reproduce. For this, they need a biological instruction that sets the basic mechanisms of the organism. How dead things without a genome become alive with genomes is one of the biggest mysteries in science. To simplify greatly, the problem is that to function the genome requires proteins, and to make a protein, a functioning genome is required. Both the body and genomes are super long molecules made up of complex blocks that are extremely difficult to assemble randomly. This is a chicken and egg paradox with several chickens and eggs. Once you have a ready-made cell, this whole mechanism works efficiently. But starting from simple inanimate things and reaching such a level of complexity by trial and error took a considerable amount of time. So how did the first living beings overcome this gap in just a few 100 million years? Most theories about the origin of life try to explain this gap by developing theories of how some primitive mixture of prebiotic molecules could effectively teach the first self-replicating substances. But we still don't know exactly how this should work. Maybe we need to think in reverse. Evolutionary clock. Imagine genomes as a book telling the story of life. Over time and the evolution of life, new characters appeared: amoebas, fish, amphibians, dinosaurs, and mammals. Over billions of years, the story of life became more and more complex. The genome can be seen as a long text with biological characters. And starting from microbes and ending with today, the main genomes, apparently, increased in complexity at a fairly constant rate. The functional genome of a fish is more than twice the size of that of a worm. Our functional genome is about twice the size of that of a fish, and so on. This is a bit more complicated, but for now, let's go with this. When we put all this evidence together, it seems that genomes double in complexity on average every 350 million years or so, as if evolution followed exponential trends. But this is even stranger. The first microbes that appeared on Earth, even if they looked simple, already apparently had quite long and complex genomes. But how could life reach such a level of complexity in such a short time? Maybe there's an interesting way to solve the puzzle. We simply impregnate our exponential clocks and extrapolate them back in time to the simplest form of life represented. Something equivalent exists in the genome, containing only a few letters. But if we do this, we will end up 10 billion years ago, more than twice the height of the Earth. This means that if life indeed developed this way, it began not here, somewhere in space. This would explain why life quickly started flourishing on our young planet. If it already exists in space, like a family, it just needs water and warmth to wake up and continue to evolve. And it would also explain that the level of complexity of the early forms of life on Earth was high. They could have been complex already because the potential possibilities could have been growing for billions of years somewhere else in the universe. But can life really be so serious? Perhaps, yes. In fact, life could have started shortly after the birth of the universe itself. The baby universe, Goldilocks. At the simplest level, life needs two things: basic chemical elements to form complex molecules and a liquid medium, such as one in which these molecules can move and interact. The liquid medium must remain warm enough to stay liquid. So when exploring life in space, we focus on Earth-like planets. located at the ideal distance from their star warm enough to maintain liquid water. But in reality, there was a time when virtually the entire universe could have been habitable. Right after the Big Bang, the universe was extremely hot. But as the cosmos expanded, it cooled down. Approximately 10 to the power of 17 million years after the Big Bang, when the universe was 1,000 times younger than today, the temperature reached a level between 100 and 0 degrees Celsius at the final temperature at which water remains liquid. So for this time window, more than 13.7 billion years ago, the entire universe, every inch of it, had the right temperature to support life. Of course, the right temperature alone is not enough for life. We also need chemical elements like carbon and oxygen, which are produced in the cores of stars. But were there stars in the very early cosmic times? Maybe yes, in regions of the universe where matter was especially dense. Such stars were very massive and exploded in just 3 million years, seeding the early universe with chemical elements, building blocks for dust, asteroids, planets, and the existence of life. Perhaps the earliest ancestors of life were more exotic and didn't even need water, but thrived on substances like ammonia or ethane, which allowed them to maintain liquid chemistry at temperatures significantly below OC. Their potential to maintain the remaining heat of the Big Bang for tens of millions of years, even after we made sure there were stars and all chemical elements. The real magic of this idea is that at the time when today's remote and hostile lands existed, conditions for life could be almost everywhere. During a period that may have lasted for tens of millions of years, primordial life could have appeared on any scale, even between the stars, sowing the universe with seeds that, after billions of years, became bacteria, trilobites, dinosaurs, and finally us. At some point, the universe cooled down below the temperature necessary for life. But some of the ancestral forms of life could continue to exist in the internal heat of early planets, frozen in asteroids or existing in cosmic dust, small seeds wandering the universe, awaiting new hospitable places to continue their civilization. If this happens, life could be everywhere in the universe. Will we ever find out? All of this sounds like a good story. And while the ideas of the independent baby universe and our exponential life clocks are reasonable, they are still speculative. Another possibility among many others trying to explain our existence today. But if life came to Earth from space, then it must have settled in other parts of the solar system as well. Perhaps there are valuable fossil remains on Mars. Maybe we will soon discover life in the warm underground oceans of Enceladus or Europa. Titan has seas, rivers, and lakes of ethane and methane, as warm as the universe when it was 90 million years old. So finding exotic life on Titan supported the idea that life could originate in a strange baby universe. So far, when we look into space, we don't see anyone like us. But perhaps it's because it took life 10 billion years or even more to reach a level of complexity that allowed it to create a technological species. Maybe there are millions of worlds full of microbes, oceans with exotic fish, and continents with strange animals. And maybe even those like us, who have only recently gained consciousness and started looking at the sky, wondering if they are alone. Life may be thriving right now in countless forms and in all kinds of environments. And if many of us shared a common cosmic position, we would all be part of a large cosmic family.